Okay, now, any questions about what we had done until now? Also, keep in mind, what Kepler's laws are just based on observation. He didn't know about any other solar system, he didn't know about any other galaxies, etc. He only looked at the solar system. So his laws are valid only in the case of the solar system. At least in the solar system, from his laws we can say that the force acting on the planet should be radial, and the force has to decrease as the inverse radius squared in the solar system only. Now let's remember what the Newton's third law was. Up to now we have only dealt with Newton's second law, and we are already using inertial reference frame. We use Newton's second law to drive this force law based on observations of Newton. But there is also a Newton's third law, which states that if the sun is exerting a force on the planet, which is proportional to this one, then the planet should also be exerting the same force on the sun, a similar force on the sun. But you see here, the force is proportional to the mass of the object feeling the force. So if there is a force acting on the sun, which also should have the same magnitude, remember the force that the sun feels should have the same magnitude, so it should also be decreasing with 1 over r squared, but it should also be proportional to the mass of the sun itself. So this law tells me that the force that the planet feels is proportional to the mass of the planet. But Newton's third law just tells me that if the same force law applies, and that's what we are looking for, so we are looking for a general force law, then the force should also be proportional to the mass of the sun itself. So the force acting on a planet should be equal to mass of the planet times mass of the sun divided by their separation squared. That is, it has to be proportional to this, the magnitude. We also know the direction. Let's say it is in the r hat direction. It is pointing, the force acting on the planet is towards the sun, and the force acting on the sun is towards the planet. And what Newton did was just put a proportionality constant. This is Newton's law of gravity. This is the planet, this is the sun, this is the force acting on the planet, and this is the force acting on the sun. And F planet is equal to minus F sun. Because they are just action-reaction pairs. Then comes Newton's next step. This law is based on Kepler's observation of celestial objects, like the planets orbiting around the sun. But Newton said that this law is valid for any object. It's not just between planets, but this law should be valid between you and your friend sitting next to you, or between now we know there are all these galaxies, between the sun and the Andromeda galaxy, etc. It is valid everywhere. Now, we still didn't discuss the first law from Newton's laws. Already we know that, okay, this is the force law. Now, if you solve the trajectory of an object under the influence of such a force, you can't actually show that it is a parabola. It has to be a parabola. But it's just, mathematically it's quite difficult, so I will avoid it. You will do it in your third year. So when you learn sufficiently more mathematical tools, you will actually drive the orbit of a planet, starting from this law. Now, of course, again, remember, Kepler's law are based on observation. Observation with a limited equipment. He couldn't have many precise equipment. Now we have many more precise devices. We can measure the position and the speeds of the planets quite precisely. And the orbits turn out to be not exactly a parabola. Of course, within the error bars of Kepler's time, they are still, ellipses. They are still ellipses, but now we know that there are small deviations from the ellipses, because basically the force that an individual planet feels is not equal to this one. Now, if you consider a planet, if you consider the solar system, this is the sun. So we have the planets going around the sun. In almost circular orbits. By the way, you have probably seen a picture of the solar system. Several pictures showing many of the planets. All the planets, except Pluto, lie on the same plane. The solar system is quite flat. If this is the sun, if this is, let's say, Mercury, then this is the Venus, this is Earth. They all lie in the same plane, more or less. There is no planet that orbits like the sun like this, except Pluto. Pluto has such an orbit. It doesn't lie on this plane. All the planets are rotating in the same direction. Moreover, even their rotations are on their own axis. If they are rotating, they're all in the same direction. Now, this is observation. Then the question is why? So is it just a coincidence? I mean, in physics, there is rarely coincidences. There should be some explanation for this one. Now, another observation which needs a bit more explanation, which we will be discussing this week. If you look at the moon, you have probably heard that we don't see the dark side of the moon, the other side. The moon always shows the same face to us. As the Earth is rotating, the moon is rotating around Earth. So as the moon is rotating around Earth, it is also rotating around itself. Its period of rotation around Earth is the same as its rotation around its own axis. So we only see the same face of the moon, not the other side. The same holds for most planets of Jupiter. The same holds for, I think, for Mercury, very close to the sun. Of course, they don't coincide with the rotation of the Earth, but they have their rotation around their star or planet, and they have their rotation around themselves. They are equal. That is what we call being gravitationally locked. So the period of rotation of the moon around itself and its period of rotation around the Earth itself is they are locked to be equal. They are almost exactly equal. And eventually, Earth is slowing down. So now Earth is rotating around its axis faster than its rotation around the sun, but it is slowing down, and eventually, if the solar system survives that long, the rotation of Earth around itself will be equal to the rotation of Earth around the sun. They will eventually be gravitationally locked. That is another thing that we have to explain.
For the Earth to lose its speed of rotation, there must be a probe acting on it. Why or what's?
We will discuss. So these are just two questions, let's say, to keep in mind. I mean, coincidences do not happen. We have to explain why the Milky Way is flat. Now, there are very few spherical galaxies, and they are quite young. Galaxies of sufficient age, they're all flat. Why are they flat? Well, let's continue with the planets of the orbit, the orbits of the planets. Now, if you look at Earth, let's say this is Earth. Now, the force acting on Earth will be just the sum of the forces acting on Earth. The total will be the force acting on Earth due to Sun, because Sun is exerting a force on Earth, plus there will be a force acting on Earth due to Mercury, plus there will be a force acting on Earth due to Venus, plus etc. All the planets in the solar system are exerting a gravitational force on Earth. So the force acting on Earth is not exactly pointing toward the sun. But the sun is huge. the mass of the sun is huge compared to the masses of the other planets. And furthermore, the other planets are, okay, they can be sometimes closer to the Earth than the sun, but they will also be away from the Earth than the sun. So they are at a larger distance, at least sometimes. Their masses are much smaller compared to the sun. So the dominant force over here is the force acting on Earth due to the sun. The other forces will give negligible effects. Only small deviations from the orbit will deviate only by a small amount due to the presence of other planets. Now we can calculate these trajectories. We have been able to calculate these trajectories. And in fact, I think it was the Uranus who was discovered because there were some anomalies in the orbit of Jupiter. So we could calculate the orbit of Jupiter using all our knowledge about the existing planets and the sun, and we couldn't explain the orbit of the Jupiter, these deviations. So we had to hypothesize that there should be another planet further than Jupiter, and eventually we found it almost exactly at the distance that we were looking for it. Then there were, of course, other anomalies due to the orbit of the Mercury. Well, how many of you are... Okay, let me see. Okay, you probably know him, right? So, Mr. Spock. Do you know where he comes from? It's the Vulcan. Yeah, he comes from the planet Vulcan. What do you know about this planet Vulcan? It's burned down. It's hot. There are no vegetation, etc. So it should be a hot planet. In fact, planet Vulcan, in the new versions of the Star Trek, planet Vulcan is in some other solar system, but originally planet Vulcan was in the solar system, in our solar system. Because there were some anomalies, observational anomalies in the orbit of Mercury. And we couldn't explain it. We could have just repeat the history in the discovery of Uranus. And we said that, okay, so to explain the anomaly in the orbit of Mercury, there might be some other planet that we don't see closer to the sun than Mercury itself. And that planet, that hypothetical planet, was named Vulcan, the planet Vulcan. But then, of course, people calculated its distance from the sun, etc., and it turned out to be that planet had to be actually inside the sun. And until Einstein, we didn't really have a plausible explanation of why the orbit of the planet is misbehaving, let's say. Now, how it is misbehaving? Now, the expectation of the planet is the orbit is more or less an elliptical shape. That is what we expect the orbit of Mercury to be. And the ellipse is fixed. Now, this fixed in the sense that the orientation of this semi-major axis should be the same throughout the centuries. If the force acting on any planet was only towards the center of the sun, then the semi-major axis had to be fixed. It doesn't change in time. It's one of the conserved quantities of the motion. But what we observe is due to the other planets, the actual motion of a planet is not this ellipse, but what it does is this semi-major axis, it also rotates around the sun. So this is the actual trajectory of a planet. Of course, here it's a bit exaggerated. So it's basically this major axis rotates around the sun. We could explain most of it. We could explain this shift in the major axis of Earth, Venus, Mars, etc. by taking into account the effects of other planets, but not of Mercury. It was not enough. The effects of the other planets was not enough. So it was the rotation of this major axis of Mercury was more than what we predicted. And then, of course, Newton came, Einstein came. He had his new theory of general relativity, and using the new theory of gravity, this general relativity, he showed that the gravitational force, you can still write down an effective gravitational force, and he said that the force felt by planets, okay, they had this 1 over r squared behavior with some coefficient, plus there's also some correction, r cubed, plus, of course, terms that go as 1 over r to the 4, which are much, much smaller. And just adding this r cubed term, we could explain this motion of this Mercury. The other terms would give negligible effect. So this is also shown as one of the successes of the theory of general relativity of Einstein. By the way, before we pass on, this is what we call the principle of superposition. Which, by the way, according to Einstein's theory of general relativity, doesn't hold. So this basically tells us that the force that the Mercury exerts on Earth is independent of the presence of the sun, or etc. Now, Einstein's theory of relativity says that there are small deviations from this. But it holds to a very high precision. Now, any questions up to here?
Newton's gravity constant is same for all systems?
That is an assumption. I mean, we didn't go to, I don't know, the next solar system and measure the Newton's constant.
This is valid for our solar system and the objects.
Then we just assume that it is valid for everything. Is this justified? Well, up to now, we didn't find any contradiction to this assumption.
This is a number. This is just a number.
This is just a number.
Why do we add these R over 3 or R over 4? What do they represent?
Well, we don't really add them. There is a theory of general relativity which Einstein developed, and according to that theory, the force acting between two masses is not really just this 1 over r squared force. The force is much more complicated than that. And the first correction, let's say, is this 1 over r cubed term. And there are all other, you can just think of this as a Taylor expansion in 1 over r. There are all the other terms which are much, much smaller. So it just turns out that to explain, you see, if r gets larger, this term goes to 0 much faster than this one. So this term is negligible already in Venus. When you consider the distance between Mercury and Venus, that second term is negligible. It doesn't have any effect, any observable effect. But in the case of Mercury, that term turns out to have an observable effect. No. If you are interested, you can take it as an elective course in your third year. Well, we will be discussing some of its basic principles. Any other questions? So this is your question. We have the model of atom, which is the false model. This is a false model. We know that it's not correct anymore. So in this model, what we have is this. If this is the nucleus, so these will be the orbits of the electron. So they're just moving in all directions. This is the solar system. If this is the sun, these are the orbits of the planets, more or less. They're flat. Now, this is a galaxy. No. Let me close the lights. This is a galaxy that just looks like the Milky Way. And you see that it is also flat. If you would just look at it from the side, just like the Milky Way, this is how the galaxies look like. Now the center has a bulge. This is how the Milky Way looks like from the side. It's still flat. Why are they flat? So what are some of the conservation laws that we have studied? Well, angular momentum. Energy is conserved. Well, the energy can be converted into internal energy. That's what's basically heating up the planets and the galaxies. But there's still the angular momentum. It is conserved. There's no internal angular momentum. The angular momentum should be conserved. So initially, if you just imagine that initially you have all these this gas. It's not flat. Such a similar gas cloud formed the solar system, a similar gas cloud formed the galaxies. And all the particles or the matter or the stars in this cloud, they're just moving in some random directions. They would be just moving randomly. But if you calculate their total angular momentum, they will still have an angular momentum. So the angular momentum, let's say it is pointing in this direction. This is the total angular momentum of this gas cloud. Of course, there will be collisions. During the collision, some of this kinetic energy will be converted into internal energy. But the angular momentum should be conserved. This should still be the angular momentum. The total angular momentum of the galaxy after all these collisions, after it loses energy. Now, in the midterm, there was also this question. So you have this ice skater. When she pulls her hands, she starts to rotate faster. Her kinetic energy increases, by the way, since the angular momentum is conserved. Energy is equal to L squared over 2I. L is conserved, L doesn't change. But if you are closing your hands, your moment of inertia gets smaller, so your kinetic energy increases. So on one hand, you have to lose, during these collisions, you lose kinetic energy. And you are heating up. That's where the energy goes to. But if your moment of inertia gets smaller, for your moment of inertia to get smaller, you have to have some more energy. But there's no energy available. So you cannot lower your moment of inertia during these collisions. In the collision between planets and the stars, etc., your moment of inertia should be more or less constant. And remember what determines the moment of inertia. So you want to lower your energy, that's the one thing you want to do, by collisions, because during the collision, these are inelastic collisions, some of the energy will be converted into the heat. You want to lower your energy, but at the same time, you don't want to lower your moment of inertia. Now, lowering your energy, you can just do it by reducing your relative velocity. So if you want, all the planets are just attracting each other. So they will be moving towards each other, but at the same time, you want to lower your relative velocity without lowering your moment of inertia. But you see, moment of inertia depends only on your distance from the axis. So on the average, the distance of these planets and galaxies, or whatever you are studying, their distance from this axis shouldn't be too large, shouldn't change, but at the same time their relative velocities should get smaller. Well, if they are so far separated, they will start moving toward each other. That's not what you want. So what you do is they just shrink along this angular momentum. You just compress them. Well, since you are not changing their distance from the rotation axis, since the distance doesn't change, the moment of inertia doesn't change, but at the same time, due to gravity, they are just moving towards each other. You cannot shrink to a point, because shrinking to a point requires almost an infinite energy. So that's why everything gets flat. That's also why, on the average, everything is rotating in the same direction. Like the planets on the solar system, like all this Milky Way, the whole galaxy is rotating in the same direction around its center. There might be just a few stars due to certain collisions. One or two might be rotating in the opposite direction, just like the Pluto in our solar system. But all the planets, all the stars are rotating in the same direction, in the same flat plane around the center of our Milky Way galaxy. So that's why most of the galactic objects, they are flat. Questions? Now let's go back to Newton. So he claimed that this law of the force law between two masses is valid for all masses. Okay, then there's one question: what is this Newton's constant? It was measured after Newton. And okay, the experiment that they used to measure this Newton's constant was the Cavendish experiment. Let me just first summarize this Cavendish experiment. The basic idea of the problem with gravity is, you see, the force is very weak. Now, why very weak? You see, if the radius goes to zero, the force becomes huge. But when we say that the gravitational force is quite weak, what we usually mean is, let's just imagine you have two protons. Let's say in a helium nuclei. There you have two protons. There is an electromagnetic repulsion between them. They have electric charge. We will be studying electric force next year. And then there is the gravitational attraction between the two. If you just take the ratio of these two forces, both of those forces have this 1 over r squared dependence. They both have this 1 over r squared. So if you take the ratio of these forces, electromagnetic force to the gravitational force, this 1 over r squared doesn't have any effect. They just cancel. So the ratio of these forces turns out to be the gravitational force is weaker than the electromagnetic force by 1 to 10 to the power 38. That is what we mean by when we say that the gravitational force is very weak. But the difference from the electromagnetic force is that, for example, when you consider electromagnetic force, it can be attractive or repulsive. When you look at neutral objects, there's practically no gravitational force. So if you take the Earth, between Earth and the Moon, there's practically no electromagnetic attraction or repulsion. But the gravitational force is always attractive, as far as we know. There's no repulsive gravitational force. So if you take a huge amount of mass, like a planet or the sun or the galaxy, in that case, the gravitational force is the only force that influences how it behaves. All the other forces become negligible because they cancel each other. But the gravitational force always adds up. That's why at the scale of galaxies and at the scale of the universe, it's only the gravitational force that is relevant. So it's the gravitational force that formed our universe that will determine what will happen to our universe, not the other forces. Now, how do we measure the gravitational force? It is so weak that we have to find a means of measuring with very weak forces. Now, this is basically the setup of Cavendish. There is this string, he used a steel one. Now, if you just take this mass, if you rotate it a bit to one side, if you release it, what it does, it will be doing this oscillatory motion. Well, oscillations are due to restoring forces, or in this case, it will be a restoring torque. If you move it to one side, the string over here will be twisted, and there will be some restoring torque, a torque trying to restore the original orientation of this mass over here. And that force is usually quite weak, a very small force. So you can measure, what you do is you just take, if there is an external torque, it's just imagine a spring. This just works like a spring. If you have a spring, by just measuring how much the spring is extended, you can measure the force that is exerting on the spring. Just like that one, if you apply an external torque on this mass, by measuring how much this rotated until it reached the new equilibrium point, you can measure the torque exerted on this mass. Well, if you know the distance at the point at which this force is exerted, you can measure the magnitude of the force. Of course, in the case of gravity, these rotations will be very small. So what is done in this Cavendish experiment is you just take two masses to balance, connected by a beam, by a rod. This is your setup. Then you attach a steel string to the center, so it will be balanced. You have this rod, you attach two masses to the endpoints. So you attach a string in the middle so that this object, this rod, can rotate freely and horizontally. And you just bring another mass. Close to one of these spheres. There will be some gravitational attraction between these two. That's what you want to measure. And you can measure it by determining how much this string rotated. Well, the rotation angle will be very small. So it will be hard to measure the rotation angle from here. But what you do is you just attach a mirror. This is the mirror you have. You just shine a laser light. It doesn't have to be a laser. It's just it can be a beam. Now, what this will do is that just imagine we are in this room. This is the mirror. You just shine the light over here, and it will move to the other end of the classroom a long distance. So even if this rotates by, let's say, 1 degree, which will be a very small angle to measure, the image of this light on the other end of the room will move a measurable distance. So we can measure how much the image of this laser light moved in the other end of the room. By measuring how much it shifts, we can determine the rotation angle of this mirror. By determining this rotation angle of this mirror, we can determine how much this mass rotated. By measuring the oscillation frequency, we can determine the spring constant of the string, this torsion constant, let's say. And from that, we can determine what is the force that this mass is exerting on this one. So it's kind of an involved experiment which uses most of the concepts that we have learned in this classroom, but you can measure very small amount of forces. And by just measuring the distance between these two masses, you can determine what the Newton's constant is. Now, of course, there will be complications. This mass doesn't exert a force on this large sphere only, it also exerts a force on this one. In that case, you have, depending on how precise you would like to be, you have to take into account all these effects. And currently, there are some experiments who can measure the mass of a truck just passing by from outside. We can measure the forces created by a truck that passes outside. So nowadays, at least, we can make quite precise measurements of gravity. Now, one problem of measuring gravity was we are saying that, okay, the gravitational force has this 1 over r squared behavior, but until the year, it was I think in 2003 or 2004, we could only verify this 1 over r squared behavior for distances as small as 1 millimeter. For smaller distances, we didn't have any measurement. For example, in the case of the electromagnetic force, we know that the electromagnetic force has this 1 over r squared behavior up to distances of the order of 10 to the power minus 18 meters. If two objects are close at the level of 10 to the power 1 part in 10 to the power 18 meters, then we know that the electromagnetic force is still 1 over r squared. Now, the current limit on the gravity is we know that we have verified that the gravity has this 1 over r squared behavior only up to distances of the order of 0.1 millimeter. We couldn't measure it for smaller distances. We don't know how it actually behaves. And some of you were asking, well, if we have more than 3 dimensions, like in the string theory, like in 10 dimensions, could it be a different theory? Well, actually, yes. If string theory is valid, if we have extra dimensions, at distances, very, very small distances, in that case, the gravity will not be 1 over r squared. So that is, in fact, one of the ways that we are trying to test whether there are additional dimensions, extra dimensions or not. But at least up to a level of 0.1 millimeter, there don't seem to be any extra dimensions. So it's kind of a verification that we are up to 0.1 millimeter, we are living at 3 dimensions. Questions?
How can there be more than 3 dimensions?
Okay, I don't want to go into it. If we go into it, we will not be able to get out of it.
I basically understand time, but the rest seems just very obscure.
Well, there's no experimental verification up to this point. So up to this point, it's just hypothesis. The basic idea, though, is that, when we think of dimensions, we imagine things that can be infinite. But dimensions can be finite, just like take this string. You can say that this is a one-dimensional object from a faraway distance. But if you go very close by, you will see that what we mean by dimension is how do you specify the position of an object. Well, if you are very far away, if you want to specify the position of an object on this one, it's enough to specify at which distance it is from my finger. So that is the only information you need. That is one dimension. But if you look at it from very close by, you will see that there's also this second dimension. So that's what they mean by we have 7 or 8 dimensions or 10 dimensions. They're small. They're not infinite, like the x and y and the z dimensions. But once you go into it, it's hard to get out of it. Other questions? Okay, let's look at one more thing. So this is one of the galaxies. You cannot see it. Okay, now better. Now it is rotating around its center. And we can actually measure the speeds of these stars as a function of their distance from the center. And when we measure them, these squares is what we observe. They are circular velocities. So we can determine the circular velocities, and as you see, we can determine them quite precisely. And as you go away from the center, it first increases linearly, then it is flat. And the radius of the galaxy is somewhere over 10 in suitable units, somewhere over here. After this point, that's the edge of the galaxy. All these dots over here are mainly of single stars that are quite far away from the center of the galaxy. Now let's see how can we predict this behavior. So this is the galaxy. Well, there is one thing we skipped. I mean, we will come back to that afterwards. I mean, if you have a shell, and if you put a mass inside this shell, it doesn't feel any net gravitational force due to this shell. Now, we will come back to this point later on. We will prove that it doesn't feel any force. But for the time being, let's just assume that. So you have this completely spherical shell, mass is uniformly distributed around this shell. Only in this case, an object inside this shell will feel zero net gravitational force. Because mainly, if you have the object over here, the shell goes all around it. There's these masses over here that pull it in this side. The masses over here, they pull it the other way around. So these two forces, they just exactly cancel each other. Now, this is our galaxy. Let's just imagine some star over here at a distance r. It is rotating around the center. Well, the orbit is more or less circular. It's almost circular. It says it's going around the circle. This is its speed. It goes with a velocity v. So what should be the center of force acting on it? It's toward the center, and its magnitude will be equal to Newton's constant, the mass, times its speed squared divided by the distance from the center. Oh, sorry. Yes, not the Newton's constant, sorry. This should be the force acting on this planet. Now, this force will be gravitational force. Should be the gravitational force. That's the only force available. So if you just imagine the distances between stars, I mean, there won't be any collisions, etc. So the only force is the gravitational force, and the gravitational force will have a magnitude, the Newton's constant, the mass of the star, all the mass within this sphere of radius r, because of course you have mass outside of this sphere of radius r, but I mean, if you imagine the stars over here, there will be also stars on the other side. They will be pulling in opposite sides, so they will more or less cancel. Divided by r squared. So we know that from this equation, the masses will cancel. V squared will be equal to m large M r over r. And the speed of the object should be proportional to square root of mr over r. Now, we will be making a very crude model. We will assume that the mass inside this galaxy is more or less uniformly distributed within this sphere. Well, the galaxy is not a sphere, it's a flat object, but we can still model it approximately by a sphere. And if it's a sphere, the mass inside this sphere will be proportional to the volume of this sphere. So let me take this. So inside the galaxy, m of r is more or less proportional to r cubed. Now, of course, there will be deviations from this r cubed behavior, but more or less it will be r cubed. So the speed of the star, the circular speed, should be, well, r cubed over r. It should change with the radius linearly. This is what we would expect naively. Of course, we made many approximations over here, but we would assume that the circular speed of the star should increase as we go away from the center. Well, this you can also say that if the whole galaxy is rotating as a rigid body, this is also what you would expect from the rigid body motion, if the shape of the galaxy is not changing as it's rotating. Out of the galaxy, you see, our star is out of the galaxy. So all of the galaxy is already inside this sphere. So all of the galaxy will be pulling our star, but that won't change. The mass of all of the galaxy doesn't change as the star moves away. So m of r is just constant. All of the galaxy is already inside my sphere. If I increase the radius of my sphere, nothing changes. So the circular speed should behave as 1 over square root of r. Because as you are going away, more and more mass of the galaxy is inside your sphere. But once all of your galaxy is inside, just increasing the size of your sphere doesn't change the mass inside your sphere. It shouldn't. So this is basically what we would expect from this very simple argument. That as we are, if this is the center of the galaxy, this is r equals 0. As we go away from the center of the galaxy, we should go, the speed should increase linearly. Of course, the mass is not distributed uniformly, so there is no sharp cutoff, but eventually it should, once we are well out of the galaxy, it should start dropping as 1 over square root of r. So this is what we would have expected. And this is what we observe. So you see, this curve over here is a more precise calculation of what we expect to observe, just using the actual distribution of mass of this particular galaxy. And this is what we actually observe. So you see, here, this is the radius of the galaxy. So at this point, we are already well out of the galaxy. They are rotating much faster than what we would expect from what we observe. Well, if they are rotating faster at a given distance, let's say at 20 kiloparsecs, they are rotating with this speed, then there should be the corresponding larger force acting on it. There should be a larger force pulling these stars toward the center of the galaxy than what we observe. Remember, this prediction is what we predict by just using the observed mass of the galaxy. If we just use the observed mass of the galaxy, that force is enough to keep a star that has this speed in its orbit. It cannot keep this star. This star is rotating way too fast for this force to keep the star in its orbit. So apparently there's some additional force acting on these stars. And that additional force, we don't know. We say that, okay, it just behaves like ordinary mass, although we don't see it. Since we don't see it, it's dark. But it just behaves like ordinary matter that we already know, that attracts, etc. So that's why we call it dark matter. But we don't actually know what it is. It might be that maybe at those huge distances, this 1 over r squared law, Newton's 1 over r squared law, might not be valid, maybe. And we might need some other law to explain this behavior. But also, Newton's Einstein theory of general relativity predicts that at large distances, the gravitational force has to be 1 over r squared. So if we say that the gravitational force at such huge distances is not 1 over r squared, then we also need to modify Einstein's general theory of relativity. And at least up to now, we don't have such a valid modification. We don't know we don't know whether it is actually just matter, just like other matter that we cannot observe for some reason, or it's our lack of understanding of gravity. We don't know. But that's when people talk about dark matter, this is what they mean. So there is this discrepancy over observed force created by the observed mass and the measured force from the circular speeds of these galaxies. There seems to be something over there. This is not the only one. There are many other observations. There seems to be something over there which creates an additional gravitational pull. Whether it's because we don't understand the gravitational laws precisely enough, or whether there's a mass over there that we don't see either in the form of fundamental particles or in the form of just invisible planets or stars, we don't know. We are still looking for it.
Lots of assumptions before we come to this conclusion. And I was thinking about why do you think the galaxies are spherical? Because they're obviously not.
Sure. I mean, you see, this calculation over here doesn't make that assumption. No, this is a more precise calculation. But even more, you see, even a more precise calculation doesn't change our conclusion. And our expectation would be that it should have more or less such a shape.
This structure will also have the R cube as an area.
No, I mean, I don't think this model makes any assumption on them. I mean, they don't make the assumption. What they take, what they measure, the observed mass. You can also measure its profile, how it changes with radial distance, how thick it is, and you can still obtain this curve. But even our simplistic spherical galaxy approximation gives a good enough description. But the problem over here is not the fit over here. You see, it's almost linear, as we expect from this crude spherical galaxy model. The problem is if you are away from the galaxy, once you are out of the galaxy, it should drop as 1 over square root of r. It's not based on any simplifying assumptions. That 1 over square root of r result doesn't depend on whether we assume the galaxy is spherical or not. Okay, so let's give a 10-minute break.